Welcome back. Today we're going to be looking at another kind of vector product. Now, last class, we were looking at the dot product. And I'll just do a quick little recap about the dot product. We called it the dot product because we used the dot to represent this multiplication operation. And it is also sometimes known as a scalar product because the result that you get from computing a dot product is not a vector, it is a scalar, right? So it takes in two vectors as inputs, so you will have A dot B. And to compute this, geometrically, you're going to multiply the magnitude of A times the magnitude of B times the cosine of the angle between these two vectors. Now, multiplying together the magnitudes here, that makes a lot of sense, right? We're multiplying vectors, so multiply how big they are with each other. Okay, but this cosine term actually turns out to be something sort of like an alignment factor that determines how aligned these two vectors A and B are with each other. So to sort of illustrate this idea with the dot product and why we care about how things are aligned, I want to have a quick example here. And the idea is, well, let's pretend that you have a car. Okay, so here's your car. And it's a beautiful hand-me-down second-hand car, but it gets you from A to B. And the car moves with some velocity to the right, just like this. But it's a little bit too slow for you. It doesn't quite have enough power. What you'd like to do is you'd like to increase the power of this car. So the way you're going to do that is, very intelligently, you're going to do the most logical thing possible. You're going to take some rocket engines, just like this, and you're going to mount them onto the car. Okay, so here we have your little rocket, and it's spewing out exhaust, and it's going to be producing some kind of force forward, right? Some kind of thrust. If you were to take this rocket and you were to mount it onto the back of your car, sort of like that, then you're going to have this rocket pushing to the right, the same direction as your velocity. Okay, so you're going to have the force to the right and the velocity to the right. So let's just sort of make a picture there. Okay, you've got a force to the right and you've also got a velocity vector to the right. Now in this case, if we do this operation, if we do force dotted with velocity, it turns out that this is equal to a physical quantity known as power, right? This is a real thing. Power is the force dotted with velocity. So when we look at this first example here, when they're both moving in the same direction, we're going to intuitively get the maximum amount of power that we can out of the rocket into pushing our car faster and faster. We're getting the biggest possible boost that we can get out of this rocket. Now, if instead we were to take this rocket and we were to mount it on the roof of our car, facing down like that, well, what would the situation be? In this case, yeah, you would have this force pushing down while the velocity is to the right. And how big of a boost, how much power are you getting out of this rocket into increasing the speed of your car? Well, pretty clearly you're getting nothing out of it. You're getting zero power out of this rocket because it's putting all of its energy and force into pushing your car down, but your car's actually driving to the right and it's not going to go down because the floor is there, right? So it's not producing any useful power, zero. So this is what we were talking about when we looked at this alignment factor. In this case, 90 degrees. Cosine of 90 is going to be 0. And so the alignment factor takes our boost and it drops it down to 0. In the first case, our angle between them is 0. And so cosine of 0 is 1. And so our power output is going to be the magnitude of force times the magnitude of the velocity. And you can't get any bigger than that, right? And of course, if you were to have your rocket at some intermediate angle between these, then you would get some intermediate amount of boost, some intermediate power out of this combination. So in a situation like this, we still have the velocity to the right, but the force vector is now here at some angle that we called phi, away from your velocity vector. So in this case, what you could do is you could decompose this force vector into component vectors, right? You could have a component vector that's parallel to your velocity. You could call that f sub v, right, in the direction of the velocity. And you would also have a component that is vertically or perpendicular to that. We could call that f sub perpendicular, right? In this case, the f sub perpendicular component of the force is going to be similar to this situation. It's going to produce 0 power, while the f sub v, or that parallel component with the velocity, is going to be like this first situation, and it is going to contribute and produce some power. It's going to give you some kind of boost to your car. But it's going to be, f sub v is going to be smaller in magnitude than the actual thrust or force vector coming off of your rocket. And so your total power is going to be less than in the first situation, right? Here you're going to be getting some medium amount of power, not the full amount, because the angle is not perfectly aligned. And whatever that amount is going to be, it's going to be scaled by this alignment factor from that angle phi. So this is the idea with a dot product, right? And when you think about dot products, you want to think about the more things are aligned, the more they boost each other, the more they multiply with each other. And if they're completely misaligned, then you're going to get 0 boost, 0 multiplication. And then if they're aligned, anti-aligned, then you're going to get essentially negative boost, right? It's going to be, if you had the rocket in front, it's going to be pushing you back, so you're going to be getting negative power from the rocket. It's going to be reducing the speed of your car. And so this is a very good sort of intuitive way to think about the dot product and why things get bigger when they're parallel and they go to 0 when they're when they're misaligned at 90 degrees. Another way to think about this is in terms of what multiplication means. So multiplication is often used when we're talking about, quantities of something. Like we have 5 apples, and now we have, if you want to multiply that by 2, well, you're going to have 10 apples, right? You've increased the quantity of something, right? It increases quantity. This is one way we think about multiplication. And when you look at the dot product, that's sort of what you're doing, right? Depending on the angle here, you're increasing the amount of power that you have. You could have 100 watts or 100,000 watts, and it depends on how big your velocity is, how big your force is, and the angle between them. But you wind up with some increase in some quantity, all right? Now today we're going to be looking at another type of vector product, and we're going to call this a cross product. Okay, and we call it a cross product because it uses a little cross or an X to be the multiplication symbol for this operation instead of the dot that we use for the dot product or the scalar product. Now the cross product is going to be sort of using a different conceptualization of what multiplication does. Let me give you an example here. Let's say you are looking at a map for a house, maybe a blueprint or something like this for a house. And what you have here is a room. And in this room, maybe you've got a table with some chairs around it, right? You've got a sofa over here. You've got a TV over here, whatever you want. It's a room, okay? Nice room. We can measure some things about this room. One thing we might measure is the width of this room. Maybe it is 4 meters wide, okay? We can also measure the length of this room, and maybe it is, I don't know, 5 meters wide, okay? Now, if we were to do a multiplication operation here, and we were to multiply 4 meters times 5 meters, what do we get? Well, we get 20 square meters, okay? Not a difficult operation, but we see what we've gotten here is a kind of area, okay? And this is another way to think about multiplication. You can think about multiplication as creating area. And this is an interesting way to think about multiplication. It's different from over here where we said that multiplication, multiplies or increases a quantity. That's one way to do it. You've got 5 apples, 2 times 5 is 10, great. But multiplication can also be thought of as creating some kind of area, like the area of a room. And this is useful because vectors are geometric objects. And so having some kind of area, a geometric area, it makes sense that this might work with vectors. So let's see how this would work. Let me take this shape here, and I'm going to shrink it down just a little bit to save up some space. Thank you. You served your job well. And put that over there. Okay, so let's say we've got 2 vectors, right? Let's get 2 vectors over here. Let's get a vector A, just like that, and we'll also get a vector B, just like that. Okay, here's vector B. Now, if I wanted to multiply A cross B and create an area, how would I calculate this area? Well, I think it's pretty obvious. If this is a 90-degree angle here, the area is going to be the area of this rectangle right here that is swept out by this vectors A and B. And the area of a rectangle is going to be equal to the base of the rectangle times the height of the rectangle. And in this case, the base is magnitude of A and the height is the magnitude of B. And if we do that, then we will have calculated this area. Okay, so this is giving us some idea of a new concept of vector multiplication, giving us an area for the object that is created by these 2 vectors. All right, now let's, this is sort of the simplest situation. Let's tweak it a little bit. Let me redraw vector A over here. So we've got vector A again. And let me draw vector B again, but this time vector B is going to be parallel with vector A. Okay, so now let's do the calculation again. What is A cross B going to be? What is the area going to be here? Well, the formula is base times height, okay, but here we can see that the height is equal to 0, right? We have 0 height here because these 2 vectors are parallel, and that means the area is going to be 0, okay? There we go. We've got 2 extremes where we have the maximum area when they're perpendicular and 0 area when they are parallel. Now let's look at the more general situation where they are at some angle between them, some general angle between them. So let me draw out our vectors again. Here we have a vector A. And let me also draw vector B, and let me draw it at some general angle, sort of like that. Sort of like that. Okay, so here now is vector B, and it's at some general angle phi with vector A, just like that. Now let's do this operation again. If we say that A cross B is going to be the area that A and B create, well, what's that going to be? What's the area here? Like, what shape are we talking about? I mean, are we talking about this triangle? No, that doesn't quite make sense, right? Are we talking about, I don't know, something like this? That doesn't quite make sense either. Instead, what we're going to be talking about is the area of the parallelogram. that is swept out by vectors A and B. And so in order to do that, I'm just going to draw the parallelogram here, and this side is parallel with vector B. And let me trim this down. Just like that. Okay, so here we've got the parallelogram that we create with vectors A and B, and we want to find the area of this parallelogram. Now, if you don't remember the equation for the area of a parallelogram, here it is. It is base times height. Okay, so it's kind of the same equation that we've been using this entire time. But the height is going to be a little bit special here, right? So we have to define the height, and the height is going to be defined as this quantity here. So it's going to be perpendicular with the base, and it's going to connect up here with the tip of vector B, and that's going to be the height of our parallelogram, okay? Now, can we find out what this height actually is? And we can. If you notice, this is a right triangle in here, okay? Where B is the hypotenuse and H is the opposite side from the angle phi. So we're going to be using then trigonometry, and we're going to use sine because H is the opposite side, right? Where sine of phi is equal to the opposite over the hypotenuse. And so from this, we can see, let me use yellow here. We can see that H is going to be equal to B sine of phi. Okay, so we can now take this equation, base times height, and we can see that the base of this parallelogram is going to be magnitude of A, and the height is going to be this quantity here. It's going to be B sine of phi. And so now we have the equation in general to calculate the area of this parallelogram. It's going to be AB sine phi. Okay, you're thinking that's great, but when I think of areas like this, I prefer to think about it with rectangles like that, not really parallelograms. They kind of seem a little bit funny. I mean, I get what you're talking about, but rectangles seem a little bit better. Well, that's okay, because it turns out that this parallelogram right here is actually a rectangle in disguise, right? So if you wanted to, you could take this parallelogram and you could chop off this triangle right here. And if you were to do that and move it to the other side like this, you would see you actually do have a rectangle. And so this rectangle, if we wanted to calculate the area, is going to be equal to the base times the height of the rectangle. And the base is this magnitude A. And the height here, well, that's also this height right here, right? It's the same. And so we still have that same right triangle. And so we're still going to get the same value that we had before for the height, and that's B sine of phi. And so you can see these two equations are the same. You can think about this as either sweeping out, A and B either sweep out a parallelogram, or they're sweeping out a rectangle where the height is equal to B sine phi. So rectangles, parallelograms, any way you want to think about it, it works out. Okay, great. I've convinced you so far, hopefully, of that. But why are we treating A as the base, right? Is there something special about A? You know, A is the base and the height comes off perpendicular to that. Why can't B be the base, right? B and A are arbitrary vectors. One's no more important than the other. And so what we can do is we can take a look and see what would happen if instead we treated B as the base instead of A. And we can do that. So let's take a look real quick. Let me delete this height vector, or height length. And let's create a new height treating B as the base. So in this case, in order to do that, we would have to treat B as the base. And so what's going to happen is it's going to go from the tip of A and it's going to come down perpendicular to B. Sort of like that, right? And so now this is a perpendicular angle over here. It's a 90-degree angle. And so now we have a new h over here. Now, in this case, we want to calculate the area. Okay, so let's do that. Area is equal to the base times the height. Good. And in this case, the height is going to be a right triangle in here. So now the hypotenuse is value a. We still have this phi and still have this h. So we can see that sine of phi is going to be opposite over hypotenuse. We can see that h is going to be a sine phi. So now, what's the base of this entire parallelogram? Well, we're saying the base is b, and the height is a sine phi. And so what we can see here is that this equation and this equation are actually the same, right? AB or BA, you're going to get the same value. And so whether you choose to treat A as the base or B as the base, it doesn't matter. Whether you choose to treat this as a parallelogram or as a rectangle by cutting that off and moving to the end, you're going to get the same value. So I hope that I've convinced you that this equation of AB sine phi is going to be the equation for the area of this parallelogram or scrunched rectangle swept out by the vectors A and B. And that's going to be the value of our cross product operation. Okay? Okay, and so now we have this equation for the area that the A and B vectors sweep out, and we can compare this equation with the one we had for the dot product, and we can see that they're sort of complementary. In the dot product, cosine of phi was seen as an alignment factor. It goes to a maximum when the vectors are aligned, and it goes to 0 when they're completely misaligned. In this case, now we're using sine, which sort of has the opposite behavior. We can think of sine phi as being a kind of orthogonality factor, where it goes to a maximum when vectors A and B are orthogonal to each other, and it goes to 0 when they are parallel, because when they are parallel, you're going to get 0 area, and when they are orthogonal, you're going to get the maximum area, and anywhere in between that, the area gets smaller because your parallelogram shrinks down as it collapses. The area shrinks down. So this is just sort of an interesting way of seeing how cross product and dot product are kind of complementary views of multiplying vectors together. Okay, are we done? No, we're not done. There's more to come. We're not done with the cross product yet. So the cross product is sometimes also known as a vector product, right? If you look at the Young's textbook, it's going to call it a vector product. And what that means is we should be expecting to get a vector result after performing the cross product operation. All right, so let me draw a couple of axes here real quick. Here's our x-axis, here's our y-axis, and we've got our vector A, and we've also got some vector B. Something like that, right? And A. Okay, so what we said is that what the cross product is doing is it is calculating some kind of area, right? Some kind of area that is the area of like a parallelogram that's swept out by vectors A and B. So if A cross B results in an area, and we saw that the formula for this area was going to be AB times the sine of the angle between them. Now the problem here is that AB sine phi is not a vector, right? There's no direction there. There's only a magnitude. That means this is a scalar. And so we're actually calculating the magnitude of A cross B. We haven't actually calculated A cross B yet. We're missing the direction component. So how can I represent A cross B as a vector? Well, a vector is going to have two properties, a direction and a magnitude, right? I think magnitude here is pretty easy. We can just say that the magnitude of A cross B is going to be equal to the area of the parallelogram. Okay, so the length of this vector, let's call it vector C. Okay, we'll say that A cross B equals C. We'll say that the length or the magnitude of C is going to be equal to that area. It's going to be AB sine phi. So that's not too bad. But what about the direction? The direction actually seems to be the more confusing property. If we want to create a vector out of the vector product or the cross product, it needs a direction. When you look at A, when you look at B, how can we possibly get a direction out of this? Well, it turns out what you can do is you can think of vectors A and B as lying on a plane, right? Vectors A and B together, they sweep out an area, and that area is also going to lie on this plane that A and B both lie on. And in this case, A and B are lying on the xy plane. But whenever you have a plane, you can always construct another vector that is perpendicular to that plane. And that gives us our direction, okay? So we're going to say that the direction of our vector product is going to be it's going to be perpendicular to both A and B, right? It's going to be perpendicular to the plane that A and B both lie on. And in this way, we can now choose a direction, and the magnitude is just going to be equal to that area that it's swept out. And so now we can create an actual vector result from our vector product. All right, let me look at how this might work in practice. Okay, so I'll draw a couple of axes here, and I'm actually going to draw a z-axis this time, something like that. Okay, so let's say we've got our x, y, and z axes just like this, and then we've got a vector A, and we've got a vector B, just like that. And we want to have a vector C. Okay, so we're going to say that C is equal to A cross B. Okay, now let me just define these vectors. Let's say that A is equal to 5 I hat and B is equal to 4 j hat. In this case, what is vector C going to be? Well, the magnitude is going to be equal to this area, right? And if these are at 90-degree angles, then it's just going to be the magnitude of A times the magnitude of B, which is 20. And the direction is going to be perpendicular to both of them, perpendicular to the xy plane. And so it's going to be in the k hat direction. And so we could draw vector C as something like this. Perpendicular to both A and B. Great, we can do it. But here's a question for you. Why not negative k hat direction? Why was C pointing in the positive k hat direction? I mean, we can easily also construct a vector that points in the negative k hat direction, right? I mean, that's also perpendicular to both A and B. So why did we arbitrarily choose the positive k hat direction and not the negative k hat direction? So in order to make this choice, what we have to do is we have to develop a kind of standard or a kind of convention. Okay, so that's what we're going to do right now. And we're going to do this by calling upon something known as the right-hand rule. Okay, now the right-hand rule is basically some kind of, like I said, a standard or a convention about how we choose this direction, because we could choose either one, but as long as we have a way to make this choice and we stick with that method all the time, we will have consistent results. And so we just have to choose. And this is how we choose it. I'm going to create a set of axes here. Something like this. Okay. So here we've got our axes, and I'm going to draw a couple of vectors on them. Here we'll have a vector A, and here we'll have a vector B. Vector B. And vector A. Okay, let me just copy this real quick. Perfect. Okay, now the way we do the right-hand rule is the first thing you're going to do is you're going to take your hand and you're going to point your fingers along the first vector, vector A. Okay, so that's what we're going to do here first. Remember, this is A cross B. So step one is to point your fingers along vector A. Okay, step two, we're going to take the same set of axes, and now what you're going to do is you're going to take your fingers and you're going to curl them towards vector B, like that. Okay, so you have your fingers pointing along vector A, and then you curl your fingers towards B, which is out of the screen, and you're going to see your thumb is pointing in a direction that's perpendicular to both of them, and that is going to point in the direction of vector C. Okay, so you curl your fingers towards vector B, and then step three is your thumb points along vector C. This is how we do the right-hand rule, okay? And so we can now draw vector C is going to be up here just like this, because that's the direction that your thumb is pointing in, okay? And so if we go back to our example over here, we can see that we're pointing our fingers in the direction of vector A, pointing our fingers in the direction of vector A, and then we curl our fingers along the direction of vector B, and our thumb points out of the screen towards the direction of vector C, and that is going to be in the k-hat direction. Okay, so this is the standard convention that we use to define the direction of the cross product. Now, I want to kind of take a closer look at this cross product direction because there's something interesting here. Okay, let's take a look at this cross product direction one more time. Let me bring down these axes just like this. Okay, here's the idea. Okay, if we have A cross B equals C, okay, then using the right-hand rule, A cross B is C, so C is going to be pointing up. Okay, we see that. That's what we just did. Great, okay, no problem. But what happens if we also want to try computing B cross A, and we reverse the direction? Okay, well in this case, now what we're going to do is we're going to start with pointing our fingers along vector B out of the screen, and then we're going to curl our fingers in the direction of vector A. And now our thumb points down. Okay, and so let's say that this is equal to vector D. And what we can say is that vector D is going to be pointing straight down like that. So this is a very, very interesting thing. What we've noticed is that vector D and vector C, they're the same magnitude, but they're in opposite directions, right? So what we could say is that A cross B is equal to negative B cross A. And this is an interesting property because normally with multiplication, we think of multiplication as being commutative. You can change the order that you do that multiplication, but it doesn't change the result. In the cross product, it doesn't work that way. Cross product is not commutative, right? Instead, we can say that the cross product is anti-commutative, meaning you actually get the opposite answer if you reverse the order of operations here. And so that's just a very interesting detail here you want to be aware of. When you do the cross product, the operation order really matters. You're going to point your fingers along the direction of the first vector, and then you're going to curl them in the direction of the second, and your thumb points in that product direction. All right, now we're almost done. I just want to now learn how to actually calculate what the cross product result is going to be in a general sense. So far, we've been dealing with vectors that are parallel to the axes, but that might not always be the case. So let's see how to do this. So there is an interesting consequence now with cross product and how we actually define our coordinate systems. Because when we use our right-hand rule in order to create the cross product, what we're actually kind of doing is we're defining how our coordinate system must work. Okay, now let me give you an example here to show you what I mean. Let's say I have a coordinate system just like this. This is X, and this is Y, and this is Z. And what that means is that along this axis, we can define our I hat vector. Here's our J hat unit vector, and here is our K hat unit vector along Z, right? I hat, J hat, and K hat. What we're saying is that using our right-hand rule, we take our right hand, and if we have want to do an operation like what is I hat cross J hat, well, we're going to take our right hand, we're going to point it in the direction of I hat, curl our fingers in the direction of J hat, and our thumb is going to point in the direction of K hat, right out of the screen, right? So that's what we see happening right here. And this little fact about how this works means this is how we define a right-hand coordinate system. And so this I hat cross J hat equals K hat is the definition of a right-handed coordinate system. What I mean is, as long as we create our axes so that I hat cross J hat equals K hat, then we're good. But if we define our axes in a different way where this isn't true, then none of the math we do is going to work out. So we always have to consistently use right-handed coordinate systems forever, for the rest of this course. Okay, so let me give you an example of another right-handed coordinate system that works. So here, let's say this is going to be the x-axis, this is the y-axis, and this is the z-axis, okay? This will work, right? Because if we take our fingers, okay, this is going to be our I hat, this is going to be our K hat, and this is going to be our J hat direction, right? So this is now J hat, I hat, and K hat. We can see that you can take your fingers, point them in the direction of I hat, and now we're going to curl our fingers back into the screen, and our thumb points in the direction of K hat. And so this works. This set of axes is a right-handed coordinate system. So that works. Let me show you an example that doesn't work. Okay, so this example works. Here's an example that doesn't work. Let's say this is our x-axis, and this is our z-axis, and this is our y-axis, okay? So now, let's say this is our I hat, this is going to be our j hat, and this is going to be our k hat. Okay, so now let's try I cross j again. We're going to take our hand, we're going to point our fingers along the I hat direction. Now we're going to curl our fingers across into the j hat direction, and our thumb is now pointing in what should be the k hat direction. But we defined our axes in a bad way, and so now it doesn't work. So if you define your axes this way, it's no longer a right-handed coordinate system, and none of the math that we do in the future is going to work out. So we have to remember to consistently use right-handed coordinate systems that are defined by this simple little equation over there. I hat cross j hat equals k hat. And this is going to bring me to another interesting point. When we talk about unit vectors, we're going to be able to do the cross products for these unit vectors. And I kind of want to do all of these cross products right now so we can get some like identities, some how these unit vectors interact with the cross product and see what happens. Well, there are 3 unit vectors, and we can multiply them, each one of them, 3 different ways. And so we have 9 different total unit vector cross products that we could look at. I want to look at when unit vectors are crossed with themselves. Okay, so for example, if I have an I hat cross an I hat, well, they're both parallel to each other, so the cross product we know is going to be equal to 0, right? And the same thing for j hat cross j hat and k hat cross k hat, they're all going to be equal to 0. So we can say that I hat cross I hat equals j hat cross j hat equals k hat cross k hat, and these all equal 0. Okay, so in the future, if we're using IJK notation, we see these operations happening, we know that the result is going to be 0. Now, what else can we look at? Well, we know that I hat cross j hat equals k hat. That's sort of by definition, right? In a right-handed coordinate system, this must be true, okay? But what is j hat cross I hat going to be? Well, it's going to be reversing the direction, so we're going to reverse the direction of our result. And so in this case, this is going to be equal to negative k hat, like that. But I kind of want to put these all together, so if we solve for k hat, we can say that k hat is equal to negative j hat cross I hat. So what I want to do is I want to rewrite this, and I want to write this as I hat cross j hat is equal to negative j hat cross I hat, which is equal to k hat. Okay, so here's another set of simple operations that we know must be equal to each other. And we can do another couple of operations just like this. Let's see what j hat cross k hat, well, we know this must be equal to negative k hat cross j hat. And what does this equal? Well, let's look at this first set of axes up here that we'll refer to a lot. That's going to be our reference set of axes. If we take our fingers and point them in the direction of j hat, and then we curl our fingers out of the screen in the direction of k hat, now we can see that I hat must be going, our thumb is going to point in the I hat direction. Okay, so this is going to be equal to I hat. And finally, we can also have k hat cross I hat, and that's going to be equal to negative I hat cross k hat. And what direction is that? Well, we point our fingers out of the screen along k hat's direction, and we curl them in the direction of I hat, and our result is going to be our thumb pointing in the j hat direction. And so that is going to be equal to j hat. Okay, so we have all of these computations done with our unit vectors. Now, why did I do this? Well, it's good to know, but what I want to do now is I want to actually calculate in I hat, j hat, k hat, component vector notation. I want to calculate the general case for A cross B. And what is this going to equal? Okay, we did this before with the dot product, so I want to do it again for the cross product. So in this case, let me write this down real fast for you. We're going to have okay, so what I've done now is I've written down the expanded version of of vector A and vector B in terms of their 3 component vectors. And what we're going to do now is we're going to perform the cross product. So now we have a total of 6 different vectors, right? 1, 2, 3, 4, 5, 6, and we're going to have to distribute them through to create all of the terms. So it's going to be 3 vectors times 3 vectors, going to give us 9 different cross product terms. And it's going to be a little bit messy, so let me write this down for you really quickly. Okay, there we go. So I've written down all 9 terms that we get from distributing all of these different vectors and cross-multiplying them together, right? So we got AXI hat times BXI hat, that's here, right? AXI hat times BYJ hat, that's here, and then this other one's going to be here. So I got all of them, okay? I just distributed everything together to get all of these terms out. Now, what I want to notice about this is that we are going to get a couple of these terms that are not going to survive. In particular, if you look at this term here is an I hat cross an I hat, and we know that's going to be equal to 0, right? So this term is going to disappear. Similarly, J hat cross J hat and K hat cross K hat, they all equal 0 because these are parallel vectors, and so there's no area between them. These 3 disappear. The other 6, though, they survive. They stick around. So now what I'm going to do is I'm going to take the remaining 6 terms, and I'm just going to rewrite them again in a different order that will help us simplify things further. So bear with me just a second, and let me get that for you. Okay, so here we go. I've written down these 6 terms now in again, just down here in a different order. So just to verify that I've got all the terms, right? AYJ hat cross BZK hat, that's going to be here, right? Plus AZK hat plus BYJ hat right here. AZK hat cross BXI hat here. AXI hat cross BZK hat here. AXI hat cross BY here, and then the last term is going to be here. Okay, so all 6 of these terms just got copied and pasted and moved over here in a slightly different order. Now, why did I put them in this order? Well, it's because they're going to simplify a little bit, right? Here we have a J hat cross a K hat, and if we look over here, we're going to see, where is that? J hat cross a K hat is going to be right here, right? So this is going to give us an I hat as our final result, right? We're going to see that this is equal to AY times BZ in the I hat direction, right? And then this is going to be here, we're going to have K hat cross J hat, which is sort of negative, going to give us negative I hat, right? So this is going to be plus AZ BY in the negative I hat direction, right? So these are both going to be in I hat. This one's negative, so what I could do is I could say this is the I hat direction, but change this to a negative sign, so I put that in the front. And now what I'm going to do is I'm going to factor out the I hat, okay? So I'm going to just factor out the I hat like that, okay? So it's going to be AYBZ minus AZBY times I hat, okay? Times I hat, just like that. And in the same way I did that, I'm going to be able to do the same thing for these other terms. There's going to be AZBX minus AXBZ, and it's going to be K cross I, which is now going to be here. That's going to give us a J hat vector, right? And over here, we're going to get I hat cross K, which is negative, which is why we have this negative sign over here. And let's do the same thing over here. We're going to have AXBY minus AYBX in the K hat direction, right? So we're now over here where it's I cross J equals K. And so what we've essentially done is we've managed to simplify all 9 of these terms into what's essentially 3 terms, right? We can now say that A cross B is equal to AY BZ minus AZ BY in the I hat direction plus AZ BX minus AX BZ in the J hat direction plus AX BY minus AY BX in the K hat direction. Okay, so we've got it. We've got a way to actually calculate exactly the magnitude and direction of what A cross B is going to be. And this is important because when we were just using simple formulas like this, there was no direction involved, right? And it's kind of hard to geometrically figure out what that perpendicular direction is going to be from the vectors A and B, because A and B can lie sort of arbitrarily anywhere within three-dimensional space. And so it's difficult to find that cross product direction unless you use I, J, K vectors and their components. Using them, we can actually calculate it. Okay, so remember, the idea here is that A cross B equals C. And in this case, we could see this AYBZ minus AZBY as being equal to the X component of C. And this would be equal to the Y component. And this would be equal to the Z component, right? So if you wanted to write down the vector C, that's a result from this cross product, this is how you would do it. These would be your X, Y, and Z components. And this sort of finalizes how we're able to calculate the cross product. Now, for me, I find that cross product is one of the more confusing concepts that we're going to be coming across in this course. If you go step by step, you kind of understand each step what's happening, and you can understand the logic. But when you wind up with this big equation at the end, it can be a little bit confusing. The AYBZ times I hat sort of makes sense, right? Because I know a component in the Y direction crossed with a component in the Z direction is going to give me something in the X direction. That's how cross product works. But this negative sign confuses me sometimes. So what I want to do is I want to just talk about this negative sign for a few minutes. Now, if you get it, if you understand it, then I think you can stop here. You've got it. But for me, okay, so for me, I kind of find the negative sign that pops up in this expression to be just a little bit confusing. So I'm going to try and give more of a geometric explanation of what this giant expression is actually meaning, right? What is it actually talking about? So let me copy this over here. And here we've got the expression. Now what I want to do also is remember that I want to label these A cross B in red and blue, just so that we can keep the colors separate when we draw this out. Let me draw a set of axes right here. Make them nice and big. And I'll bring in my z-axis just like this. And that should work. Okay, so here's my x-axis, my y-axis, and my z-axis, okay? Now what I'm going to do is we're going to assume we have some arbitrary vectors a and b, and we're going to cross-product them together to create our cross-product c, okay? Now, we represent a and b using component vectors, right? So we're going to assume that a has some component vector in the x direction, like this, right? So this is going to be a sub x, and then it's going to have a component vector in the y direction, like this, okay? So this is going to be a sub y, and again, we'll do the same thing in the z direction, something like this, and this will be a sub z. Now at the same time, we also have vector b. So vector b is also going to have some kind of x component, right? So here is b sub x, and it's also going to have a y component of some kind. So here we are. Here is b sub y, and finally there's going to be a z component. Let's just offset it a little bit here. So here's going to be the b sub z. Okay, so these are the three components of both vectors, and you multiply them together and you get 3 times 3 equals 9 different cross products, right? But when you do the cross product of, say, b sub x and a sub x, you know you're going to get a value of 0 because there's no area. These are parallel vectors, and so there's going to be no area that they sweep out. So really, there's going to be 3 of those pairs, this pair, this pair, and this pair, that are going to give you a cross product equal to 0. So out of the 9 total cross products here, we're going to have 6 that have an actual value. Okay, so let's look at this first term over here where we're looking in the I hat direction, where all of these values give you an answer that in the I hat direction. Okay, so first we're sort of going to do the right-hand rule backwards, right? We're going to point our thumb in the I hat direction. Okay, so this is the result that we want. Now, in order to get a result in the I hat direction, we're going to be multiplying, you can see y and z components, okay? Y and z components, when they cross together, you're going to get something in the I hat direction. So a always comes first. So if we cross ay with bz, we're going to get something in the positive I hat direction. And so that's what we have here. We have ay that winds up being crossed with bz, and that's why this is a positive number here, because the result is going to be a positive I hat direction value, okay? But you can see from this graph, we also have an AZ component and a BY component. So A always comes first. We're doing A cross B. So we're going to now point our fingers out of the screen in the Z, along the Z axis, right? So we're going to have AZ, and we're going to cross AZ with BY, which is now up, and we're going to see that we now produce an answer in the negative I hat direction. And that's why we must have a negative sign here, because our answer is going to be in the negative I hat direction. Now we're assuming all of our components here are positive values, right? That all of these components here are in the positive y axis, the positive x axis, the positive z axis. Now in real life, these components might be negative, but in that case, there'll be a negative sign somewhere in here, and so the signs will actually flow through correctly, and we'll still get the right answer. So this geometrically explains why we have this minus sign. We can look at the same thing for the y and z components for this vector c, right? So for example, for cy over here, you're going to point your thumb in the j hat direction. That's your final result. And you can see when you point your thumb in the j hat direction, you're going to have to cross multiply x and z components, right? X and z components. So if you have something in the AZ direction, right? The AZ direction, and you're going to cross that with the BX direction, that's going to give you a positive J hat value. And so that's why this is positive, right? Now, we also have an AX direction and a BZ direction. So now if we have our AX component, we're pointing in our AX component, right? And now we want to cross into the BZ, which is out of the screen. Now we get a negative J hat value here. And so that's why we have a negative sign right there. So by the same exact logic, you can step through it. You're going to get the negative sign over here and a positive sign for here when you're looking at the K hat direction, the CZ component vector over there. So I hope that gives you some kind of geometric intuition about why there's a negative sign in the middle there, right? You have AY and BY components as well as BZ and AZ components. You can cross AY and BZ or AZ and BY, and that's going to reverse the direction. All right, so that reverse direction is taken care of with the negative sign. Now we can contrast this really quickly with what we saw with dot product, right? So when we have A dot B, in this case, the value we got was AX BX plus AY BY plus AZ BZ, right? Now in this case, there's no IJK vectors that come through because this is a scalar product. We get a scalar at the end, but the idea is the same. You have originally 3 component vectors for each vector, so that's a total of 6. You're going to have 3 times 3, you're going to get 9 different dot product terms, but a dot product between, say, AX and BY, well, that's going to be 0 because these vectors are perpendicular. And for dot product, perpendicular multiplication is going to cancel out to 0, right? Because dot product is 1 when they're parallel and 0 when they are perpendicular. So a pair like this would result in a 0. And the only vector pairs that actually flow through that don't cancel out are going to be the ones that are aligned. So AX BX will give you a value, AY BY will give you a value, AZ BZ will give you a value. All of the other terms that you multiply through cancel out to 0. And so that's why this becomes our final answer here for the dot product. So that's sort of a good comparison here at how the cross product and dot product work sort of geometrically with component vectors. Okay, there we go. This is a lot of information. Cross product itself is not too difficult to compute, but I think conceptually understanding what it is, that's where the work is. So hopefully this lesson has helped you understand cross product a little bit deeper. What we're doing is geometrically is we're taking 2 vectors and we're finding the area that they sweep out, and that becomes the magnitude of a vector that's going to be actually perpendicular to both of these initial 2 vectors. It's going to be perpendicular to the plane that they lie in, and the magnitude is going to be equal to the area that they sweep out. And using IJK notation, we can expand everything out and come up with a formula that allows us to get exactly and compute exactly that magnitude and direction. If you do still have questions about that, please leave them down in the comments below so I can see them and I can try and help you out. I'm going to have a couple of questions and exercises that you can do. There's a link in the description so you can download that PDF. Do a couple of exercises, and in the next lesson, we're going to go over those exercises. They're going to cover dot product as well as cross product. So a lot of work there. But these are foundational mathematical concepts that allow us to now manipulate and work with vectors in 3-dimensional space. So they're going to be very important. If this did help you out, I would appreciate it if you could give me a like and a sub, because that's going to help me out a lot. And I hope to see you in our next lesson where we go over the exercises for cross and dot product. Thanks a lot. Bye-bye.